Hello everyone and welcome back to Clinical Cousins YouTube channel. Today we're going to go over how to find the electrical axis of the heart on the XY plane with precision. So this is a continuation in our EKG series where we're talking about how to find the electrical axis of the heart. We've gone over normal, we've gone over left axis deviation, right axis deviation. So if you haven't watched those previous videos, I recommend that you give them a quick view so that all of this will make sense when we start putting it together. So basically, I've come up with a way, and this is just a very quick way to find the electrical axis with extreme precision. So we must use FDA, and it's not the Food and Drug Administration. We must find, determine, and adjust. So if you follow along to the end of the video, I promise you it'll all make sense, and this will be your new favorite way to find the electrical axis of the heart with precision. So because we're only talking about the XY axis or the coronal plane, we are only looking at the hexaxial leads, meaning we are only looking at leads 1, 2, 3, AVR, AVL, and AVF. So for now, forget the chest leads in our EKG. We're just going to focus on those that are concerned with the coronal plane. So first, we must find. Specifically, we must find the one isoelectric lead out of all of our leads that we have available. So remember that the isoelectric lead is the lead that is the most neutral, meaning that this lead is neither very positive nor very negative. So basically, we are finding the EKG equivalent in our leads of Switzerland, right? It doesn't choose sides. So this will be the lead with the lowest voltage, or the lead that is the most flat. So why is the isoelectric lead even significant? Because we know from our previous videos that if a few vectors head toward a lead, shown here in purple, if a few vectors head toward a lead, then a positive deflection will occur, and if a few vectors head away from a lead, then a negative deflection will occur. So the cool thing about the isoelectric lead is that if these happen in equal amounts, in equal positive and negative deflections, then our lead will end up being isoelectric, meaning it'll be the most neutral. So remember, if our vectors are headed toward a lead, it gets excited, it has a positive deflection. But if we have some more vectors that are headed away, our lead becomes sad and it has a negative deflection. This is why the isoelectric lead is so important. It tells us the average or the general direction of our axis. So in our example, the isoelectric lead is lead 1. You can see that lead 1 is the most neutral or the most isoelectric, meaning that it is neither very positive or it is not very negative. Okay, so we've done step 1. We find the isoelectric lead. So next, we must determine the quadrant. So this is exactly what we did in our previous videos. You're probably very good at it by now. So all we have to do is look at lead 1 and AVF. In our example, we can see that the QRS in lead 1 is positive. I've drawn it here just to blow it up for you a little bit. We see that the QRS in lead 1 is just a little bit more positive. So we know that we are headed leftward. Also, the QRS in lead AVF is also positive. So we know that we are heading downward. So we have just determined that the axis is headed toward the normal quadrant, right? It's headed leftward and downward, so it must be in this normal quadrant. Okay, so our last step is to adjust. We need to adjust the axis based on the isoelectric lead. So we already know that our isoelectric lead is lead 1. And we know from our previous videos that lead 1 has a positive end at 0 degrees and it has a negative end at 180 degrees. We already know this. If our axis is isoelectric in lead 1, it means that the average of all of the vectors point toward the middle of lead 1, meaning that there are an equal amount of vectors that pull the axis toward the positive eyeball, and there are an equal amount of vectors that pull the axis toward the negative aspect of the lead. Well, wait a second, how do we know if this is talking about pointing toward the top half or the bottom half of our lead 1? Well, we know that the axis is in the lower left quadrant, meaning that it must be pointing towards the bottom, right? This is a general idea of where our axis is pointing. We know that it is likely pointing toward 90 degrees. It must be pointing toward the bottom. So what I like to imagine this as is like a tug of war, but the flag is in the middle because both teams are equally as strong, right? It's isoelectric. It's neither positive nor negative. So what is the result? We have an axis that is in the middle of lead 1, or it is perpendicular to lead 1, meaning that it forms a 90-degree angle with lead 1. Well, what is the middle? What is the average of lead 1, right? It's isoelectric. We know that it's headed toward and away from lead 1, but what is lead 1? Well, we know that lead 1 is between 0 and 180 degrees. So what is the middle of 0 and 180? This is 90 degrees. So now we know that the axis is about 90 degrees, and what we need to look for now is the amplitude or the height of the QRS complex in lead 1 to adjust our axis and make it super precise. Remember, we found the isoelectric lead. We know that because it's isoelectric, it's perpendicular, so it's about 90 degrees. We know this because we know that the quadrant is lower left. So we have to memorize some rules, okay? These are the only rules we have to memorize. If the QRS complex is twice as positive as it is negative, we add 20 degrees towards the positive end. Now, if the QRS is positive, but it's not twice as positive, then adjust by adding only 10 degrees. Now, if the QRS is negative, but not twice as negative, then adjust by adding 10 degrees toward the negative end of the isoelectric lead. And lastly, if the QRS is twice as negative as it is positive, it's twice as deep as it is tall, then adjust by adding 20 degrees toward the negative end of the isoelectric lead. Wow, you're saying to me right now, wow, that was a lot of information. That makes no sense. Well, pay attention towards the end. I promise you're going to have a light bulb moment. In our example, okay, the QRS in lead 1, I've blown it up for us right here. It is positive, but is this twice as tall as it is deep? No, it's not. So we are only going to adjust by moving our axis 10 degrees this way toward the positive end of the lead. So why did we do this? Because our isoelectric lead is telling us that our axis is around 90 degrees, right? It's isoelectric, meaning that it's going to be between the positive and negative, and it's going to be about 90 degrees. But it's also telling us that our positive vector tug of war team is just a little bit stronger, right? It's just a little bit more positive than it is negative. So we add 10 degrees, making our final axis 80 degrees for this EKG, and we know that that is normal. So that was a ton. But what did we just do? Assuming you know all the steps, we found the isoelectric lead. Okay, easy. We determined the quadrant. Easy. Then all we had to do was make it accurate by adjusting the axis either 10 or 20 degrees this way or 10 or 20 degrees this way based on if the isoelectric lead was more positive or more negative. So all we did was adjust the axis based on which vector tug of war team was stronger. So in our case, we found that the positive tug of war team was just a little bit stronger than the negative tug of war team. Now, was it twice as strong? No. So we only added 10 degrees toward the positive end. So imagine a bunch of guys over here, right? We know that our axis is 90 degrees. Imagine a bunch of guys over here, and they're just a little bit stronger than a bunch of guys over here. So we added 10 degrees to make this a final axis of 80 degrees, which is normal. So just to recap, what did we learn today? We learned the normal axis is -30 to positive 90 degrees. And we know to determine the electrical axis of the heart with precision, all we need to do is find, determine, and adjust. So what did we do? We found the isoelectric lead. This was lead 1. Then we determined that the quadrant that the axis was in, right, a very general assumption of where it was at was the lower left quadrant, which is also known as the normal quadrant. So how do we do this? We know that it's positive in 1, so it's headed leftward. We know that it's positive in AVF, so it's headed downward. We know that the axis is somewhere in here. It's not very precise, but we know that it's somewhere. So now the last step that we did, we adjusted the axis based on the isoelectric lead. So we know that the isoelectric lead gives us a general direction of where our electrical axis of the heart is going. So in our case, our isoelectric lead was lead 1. We know that lead 1 has a positive end at 0 degrees and a negative end at 180 degrees. So which way is the axis pointing? Well, we know that it must be in the left lower quadrant, so we know that it is going to be perpendicular to lead 1, which means that it's going to be 90 degrees. So this isn't good enough for us. We want to be extremely, extremely precise. So our last step was to adjust this value right here toward the positive or the negative end. So all we had to do that was, which is our stronger tug of war team, right? So we zoomed in on this, and I drew it right here for you guys. So the only rules we had to memorize are, is our QRS more positive or more negative? Okay, we know that it was more positive. Okay, so how much more positive was it? How strong was our positive tug of war team? Well, is it twice as strong as the other team? No, it's not. So logically, we must know that we must add only 10 degrees. What does this mean in simple terms? It means that the positive tug of war team over here was just a little bit stronger, right? It means that the majority of the electrical activity of the heart is headed just a little bit more toward lead 1. So what do? We just adjusted by adding 10 degrees toward the positive end of the lead. So please tune in next time where we actually incorporate the z-axis and we put it all together. As always, thank you for taking the time to learn with us today, and remember to like and subscribe for more content.